Good day, Math 30-1s. Today we continue our Chapter 6 conversation about identities. And last day we learned Pythagorean identities, which are on our formula sheet as sine squared plus cos squared is 1, 1 plus tan squared is secant squared, and a 1 plus cotangent squared is cosecant squared. So these three were introduced last day, and we really talked about the verbs simplify and verify, and we learned how to maybe apply these a little bit and start to get a little bit comfortable with them. Today we learn the rest of our formula sheet, which has something called sum difference formulas, where our angle is added with another angle. We have double angle formulas, which aren't as helpful in terms of calculating angles, but it is helpful in terms of swapping out and doing conceptual problems, very algebraic problems, where we're trying to simplify. So there are double angle formulas and sum and difference formulas. And these are very, very helpful if we're looking at trying to apply them to angles that we're not always maybe used to being able to deal with. So if I were to ask you to evaluate sine of 30 as an exact value, you would say, well, of course, on the unit circle, the y value at 30 degrees is 1/2. If I were to tell you to evaluate sine of 15 degrees as an exact value, you would say, I can't do it. I have to use my calculator. There is no way. Now, as of today, I get to say we can do sine of 15 degrees. We can do sine of 75 degrees. We can do a few more angles that can be connected with angles we know. What I mean by that is that we can take some angles like 15 degrees and 105 and 195 and 75, and we can somehow use angles that we're used to, 30, 45, 60, 135, 120, 150. We can use these angles to help us out. So by asking about cos of 15 degrees, I can create 15 from angles we know. I could say 45 minus 30. For 105, I could say that I could recreate 105 using angles we know with maybe a 45 plus a 60. I know information about those. Sine of 195. I could create 195 a couple ways. I could say 150 and a 45. I could say 135 and 60. And there's a few ways to create 195. 75, we could say 30 plus a 45. Now, it's important to know that I'm not saying that it's a sine multiplied by the angle. That's not what trig is. It's not sine times 45 plus sine of 60. It's not a product. There's formulas on our formula sheet that say, if you're adding two angles together for sine, you could rewrite this formula out and it will all work out quite nicely. I worked out an example to clarify how to evaluate a question like this. So if you were asked to determine the exact value of sine of 75 degrees, we're not typing that into our calculator. It will give us a decimal. We can say, 75 might be something that I could create using angles we know. You could say that sine of 75 is a sine of 45 and a 30. On the formula sheet, you would see something like this. Now, you'll get to see alphas and betas, but the letters are the same, essentially. And so when you see sine of addition, you're going to see sine of A, cos of B, cos of A, sine of B. Basically just sines and coses and A's and B's, where A is 45 and B is 30. So if you can look at that and swap out sine 45, cos of 30, cos of 45, sine of 30, and then evaluate. What is sine of 45? 1 over root 2. Cos of 30, root 3 over 2. Cos of 45, 1 over root 2. And sine of 30, 1/2. Multiply those together and you get root 3 over 2 root 2 and a 1 over 2 root 2. Add together those common denominators. Denominator stays the same, and your root 3 plus 1 stays on top. There is an exact answer for sine of 75 degrees, something we would have thought was unrealistic before. This also makes Chapter 4 look a little less impressive because we're now evaluating 4 questions in one. So this is our expectation as of right now, that we can get an exact answer. But there's an even second step. an extension. If I were to ask you to rationalize the answer, which is an expectation in this curriculum, where, as it says, quote, students are expected to leave answers in rationalized or unrationalized forms, we might be expected to take that radical and make it not appear on the bottom. To do that for a monomial denominator, where there's no addition or subtraction happening, we can multiply the top and the bottom by the radical. So what we have on the bottom is a regular 2 and a regular 1. A root 2 and a root 2 multiplied together makes a root 4, or a 2. On the top, there is a distribution that occurs. The root 2 does have to multiply by the binomial, which makes a root 2, root 3, root 6. Root 2 times 1 makes a root 2. Tidy up the bottom, and what you are left with is a 4. Now again, root 6 and root 2 don't add together. They are not like terms, but the 4 does tidy up. And this is a rationalized form of the exact answer for, as we saw before, sine of 75 degrees. Now it's worth trying something like sine of 15 degrees, and you're more than welcome to pause the video and try this, but you're looking for some way to make sine of 15, and this would be probably sine of 45 minus 30. To which you would look at your formula sheet and say sine of subtraction. Sine of A cos of B, sine of A cos of B, minus cos of A sine of B, to which we can evaluate 1 over root 2, cos of 30, cos of 45, sine of 30. We end up with a root 3 over a 2 root 2 minus a 1. A very similar answer to what we saw for sine of 75 degrees. The only difference was there was an addition on the top. But here is an exact answer, unrationalized, but again, we have the skill to rationalize if needed. Some questions might start to feel a little more challenging, and I did say you can think degrees if you needed. Sometimes you see something like pi over 12 and you're thinking, pi over 12? That's not a pi over 6 or a pi over 3 or a pi over 4. Not a lot of people are maybe strong enough with fractions to say, you know what, this is technically 3 pi over 12 minus 2 pi over 12. And both of those angles are nice numbers. This is technically pi over 4, or 45 degrees. Technically, this is pi over 6, or 30 degrees. And I just figured out a way to get pi over 12. Really, this is the exact same question as I did above. The exact same question. But that 15 degrees and the pi over 12 look very different. So I'm not going to redo this one because I've already done it. But when you see pi over 12, not everyone's going to recognize that it's half of pi over 6. So what I might suggest is ensure you know how to convert from radians to degrees, change it to 15, and then think of a 45 minus a 30. Now, tan of 195 was once asked on a diploma, and it actually said, leave your answer in this form. And that's all you're given. In the numeric response boxes, what is A and what is B? That's sort of it. Tan of 195 can be created like we saw on the front. 195 can be created from one of those. One of these works out to be a little bit easier than the other. One of them turns out to be a little bit more challenging. You don't really know it until you try, but the 135 and the 60 actually turn out to be a little bit simpler, only because of less fractions. And I'll comment in a moment why the 135 and 60 turns out to be a little bit more simple. But when you look at your formula sheet for maybe tan of, and I'll do the simpler one this time, 135 and 60, and I'll comment on what could be different about the other option. But if we're looking at tan of 135 plus 60 on our formula sheet, tan of addition is written as tan of A plus tan of B. Tan of A plus tan of B, all divided by 1 minus tan of A tan of B. Alright, tan of 135 on our unit circle we're thinking tan of 135, 45-degree reference angle. You have the same number x as y, 1 over root 2 and a 1 over root 2, but one of them is negative. So tan is y divided by x. So y value divided by x value. 1 over root 2 divided by negative 1 over root 2 is negative 1. Tan of 60 is a little bit more complicated. Your y value is the big one, root 3 over 2, and we are dividing by an x value of 1/2. If you divide those two numbers, you end up with a root 3. I'm not going to teach dividing fractions in this lesson because we talked about that in the previous lesson and tricks and strategies to do so. We have the same two values on the bottom, 1 minus negative 1. Change that to a plus 1. Tan of 60 is a root 3. So what we're left with is a negative 1 plus a root 3, all divided by a 1 plus a root 3. Negative 1 plus root 3 over 1 plus root 3. That really doesn't look like we could put this in our numeric response boxes as a minus root b. Why? Well, they asked for it to be rationalized without actually saying so. How do you rationalize a denominator which is a binomial? Throw in another big word, we're going to use conjugates. So the conjugate of the denominator is what we need. The conjugate is the exact same binomial with a different sign in the middle. So we're going to multiply the top and the bottom by the conjugate of the denominator in order to rationalize. Again, lots of big words. I'm going to focus in on the bottom for a moment. There is 4 arrows happening when we multiply a binomial times a binomial. The good thing about conjugates is we only need to worry about the first and the last connection. 1 times 1 is 1. Now reminder, y, we don't have to worry. 1 times negative root 3 is a negative root 3. A root 3 times a 1 is a root 3. A negative root 3 and a positive root 3 would cancel out. They always will with conjugates. So we get to skip the middle terms and say the last number times the last number is a negative root 3 times root 3, root 9, or regular 3. On the top, we do have to multiply all 4 brackets, all 4 terms together. Negative 1 times 1, negative times negative makes a root 3, root 3 times 1 makes another root 3, both positive, and a negative 3. So what we're left with is a negative 4 plus 2 root 3's over a negative 2. Again, not quite like the top, but it seems like we're closer. Just like in the quadratics unit, we're at this place where we have a bit of a shared denominator. And all 3 of these numbers need to connect and reduce at the same time. Negative 4 divided by 2, 2 divided by negative 2, all of those are divisible by a negative 2. And if we divide by negative 2, we have a 2. Divide those, we have a negative 1 root 3. This all of a sudden looks very much like a minus root b, and in the numeric response boxes you would place a 2 and then a 3. Final answer. All for 1 mark or nothing. A big question. That's as complex as a question could probably get, and that is not very simple. Now, if we had chosen the other option to get to 195, so had we chosen 150 and 45, the only difference is that when you're dealing with tan of 150 has an x value divided by has a y value divided by an x value, and the only difference is that when this reduces, you're left with a fraction. So instead of seeing root 3, you'd see a 1 over root 3, and there's an extra fraction to deal with, and so that is something that maybe you'd like to try. For formulas in reverse, sometimes you can be given a question, and I'll make this a little bit more convenient. What if I were to say sine of 48 cos of 18 minus cos of 48 sine of 18, and I say try this without a calculator, to which you might say sine of 48, that doesn't seem very convenient. But when you're looking at a sine times a cos minus a cos times a sine, there are formulas that can go the other way. sine times a cos minus, maybe the second one, sine times a cos minus a cos times a sine. Hey, that's actually sine of subtraction. This is actually sine of subtraction. 48 minus an 18 is actually sine of 30 degrees, which I know is 1/2 from my unit circle. All of this is just a half, 0.5 would come out. So it's a way of sort of working backwards. When we talk about double angles are a bit of a strange thing. What we're doing is we're considering the angle and its connection to half of its angle. Now, sine of 120 degrees is equivalent to saying sine of twice 60 degrees. Now, that's not anything fancy. That's just breaking the 120 up into 2 times 60. So there are formulas in our formula sheet that allow us to take sine of 120 and evaluate 2 times sine of half that angle, 60, cos of 60. Now that's not the most helpful thing to be able to say sine of 120 is 2 times sine of 60, cos of 60, but it will be more helpful a little bit later on in more algebraic simplifying and substitutions. But there are some questions that make us think a little bit deeper about this. Like if you knew that, and I have to change this question, if you knew that secant was 5/3 and that sine was negative, and I asked you what is sine of 2 theta, cos of 2 theta, and tan of 2 theta, we could ask, well, how is this supposed to get us these? First thing to do is ask, well, what information might we need to answer the question? On the formula sheet, you're looking for sine of 2 theta, and that would come 2 sine theta cos theta. So answering about a big angle, we can actually use a smaller angle. For cos of 2 theta, this is going to be a bit of a challenge for some because when you look at cos of 2 theta, there are 3 choices. One of them is a cos squared minus sine squared. One of them is a 2 cos squared minus 1, and one is a 1 minus 2 sine squared. For tan of 2 theta, there's only one option, and it is a 2 tan theta divided by 1 minus tan squared theta. To be honest, this might look a little bit familiar from your sum difference formula. All that someone did is say, hey, what if these two angles were the same, theta and theta, and then you've got tan of theta plus tan of theta is 2 tan theta, and 1 minus tan squared of theta. In fact, a lot of these double angles formulas come from the sum and difference formulas. Anyways, so we need to know what sine of theta is. We need to know what cos of theta is to answer this question. You might be thinking, well, maybe I can try to get an angle or get more information from what we're provided. What we do know is that sine is negative. We're in the bottom somewhere. Y is negative. We also know that secant or cosine is positive, here or here. We're in the 4th quadrant. So let's draw out this information and say secant is 5/3. So not cosine adjacent over hypotenuse, but hypotenuse over adjacent. We're flipping cosine. So hypotenuse over adjacent. This is in fact a 3, 4, 5 triangle. Or you could do Pythagoras to get a 4 in a negative direction. Now that we know that sine is negative 4/5, we know that cosine is adjacent over hypotenuse, and we know that tan is opposite over adjacent. We actually don't need to figure out what theta is, which you might be thinking we need to do, because I can actually swap out the entire sine of theta with negative 4/5. I can bypass getting the angle and swap out sine of theta with negative 4/5. I can bypass getting the angle and swap out cos of theta with 3/5. And when we multiply 2/1 times 2 other fractions, we get 2 times 4 times 3 and a negative 24 over a 1 times 5 times 5, 25. Don't put that 2 on everything. There is sine of 2 theta. Choose any one of these and you'll get the same answer. I'll maybe choose the top one just because it's in order. Cos squared, 3/5 times 3/5, minus sine squared, negative 4 over 5 times negative 4 over 5 is positive 16 over 25. Subtract those together and you get a negative 7 over 25. And for 2 times tan of theta divided by 1 minus tan squared, we have a nice fraction to deal with. We have a negative 8 over 3 divided by 9 over 9 minus 16 over 9 makes a negative 7 over 9. To which we can maybe do some flipping of fractions and reciprocating and changing it to a multiply, or as I've mentioned in previous lessons, the denominator can come up to the top, this denominator can go down to the bottom, and we'd end up with a negative 8 times a 9 divided by a 3 times a negative 7, and things would cancel slightly. That maybe becomes a 3, to which we can sneak in at the very, very bottom as a final answer. Negatives cancel, and 8 times a 3 divided by a 7. Final answer. So this becomes a little bit more conceptual, that we're not really using our calculator to approach, but it does take these double angles into some sort of meaning. Lastly, going backwards and simplifying new identities. If I were to give you something like 1 minus 2 sine squared of 60, we're supposed to start to see some familiarity. Now, we've seen some double angle, some Pythagorean identities where if you see a sine squared sitting next to a 1, maybe that's supposed to stand out and look familiar. If you see a cosecant squared with a negative 1, maybe that's supposed to look familiar, and you look on your formula sheet. You see these weird formulas for addition and subtraction, and that's supposed to look familiar. And the double angles are supposed to again start to look familiar. 2 sine cos, cos squared minus sine squared, 2 cos squared minus 1, 1 minus 2 sine squared, and this weird 2 tan all over a 1 minus tan squared, all double angles. These are supposed to look familiar. 1 minus 2 sine squared. That was the second last thing I said. 1 minus 2 sine squared. We can swap that out with cos of twice the angle. Cos of twice that angle. Twice 60 is 120. That's all I'm wanting to do. I don't want to evaluate, I just want to simplify. Cos times cos plus sine times sine. Cos times cos plus sine times sine. That's the bottom one, cos of subtraction. Cos of subtraction. The two angles are 3x and x. This could tidy up to become cos of 2x. Those are like terms. And lastly, 10 sine cos. You're saying, well, that kind of was like the 2 sine cos, but not a 10 sine cos. There's always little extra tricks you can do, like saying, well, technically that 10 is a 5 times 2 sine 60 cos 60. And if I just focus in on 2 sine cos for a moment, I can swap that out with sine of twice the angle. Sine of twice the 60. And that could sit next to that 5, which is just hanging out the whole time. So really this mathematically is the same as 5 sine of 120. Now there's going to be lots of really challenging questions in here that get you to think about factoring and common denominators, and especially as you get into numbers like 8, 10, 15, and 20, you're really going to get challenged. If you need, be sure to visit bevfacemath.com and log in using your school address, and the worked out textbook solutions are on there, bevfacemath.com. Good luck in your sum difference, double angle identities, as we include those with our Pythagorean identities, because tomorrow we move on to proving identities, and all of our comfort with this will start to make sense. Good luck.